Hi, everyone. We are the Slime Mold Network Optimization Group. I'm Olivia, and the rest of our group includes Lexi, Katelyn, and Kevin. So as industrial engineers, we learn a lot about how to optimize networks. So we decided to move towards bio-inspired algorithms to see how nature can optimize real-world networks, especially since they are understudied and more unbiased than other methods. To solve this problem, we have been experimenting with slime mold. Slime mold is a single-cell amoeboid that forms networks connecting discovered food sources. Slime mold is different because it grows in the most efficient way possible, taking into account all of its environment and finding the most optimal route to its food source. So our motivation behind solving this problem is that using slime mold to find the most optimal route is more sustainable than previous algorithms out there, especially since it has a strong robustness against the change in environment. Applying bio-inspired algorithms to real-life applications will expand modeling capacity and allow current systems to be verified, saving both time and resources. So typical methods used for solving optimization problems in the past require immense computations, which are hard to use for larger scale problems. However, bio-inspired algorithms are computationally efficient alternatives. Another research study we looked into was a Japanese research lab that used slime mold to imitate Tokyo's railway network with almost 100% accuracy. This allowed us to confirm that we could apply our results potentially in the real world. Throughout our experiments, we compared our slime mold data to existing algorithm research like Dijkstra and the minimal spanning tree to determine accuracy and efficiency for our model.
Our main contribution is the advancements we were able to implement in experimentation, including data incorporation. We successfully incorporated demand, distance, and blocking in our experiments, which included the sizes and distances of the networks being relevant to current supply chain scenarios. Through our control variation testing, we ensured the environment in which the slime mold grew remained as sterile as possible and limited mold growth. Our data incorporation consists of a GUI visualization of each network we designed, along with node Excel mapping and further comparing the efficiency of the networks created by the slime mold by utilizing other algorithms. The scientific component to our project has been determining the optimal growing procedure for slime mold given the conditions and resources we were able to provide in a non-laboratory setting. Several initial experiments were based around validating the control variables with the main goal of creating an environment for the slime mold in which it would grow best in and allow us to achieve the most accurate results. We monitored each network at least 3 times a day with no more than 8 hours in between each checkup to determine if it was growing as expected. Initial experimentation also included working with fixed and moving targets and studying the pattern recognition of slime mold. This helped us learn a lot about slime mold very early on. Control variation testing consisted of working with different locations, water sources, materials, and timing. After a few failed experiments, which you can see to the left, we discovered that upkeep is a vital component in ensuring the success of these experiments. Overall, our control variation testing has allowed us to establish the best environment for slime mold to grow in. Ultimately, slime mold flourishes in moist, dark environments at room temperature. And here you can observe a demonstration of the way slime mold grows with GIFs of 2 of the experiments we conducted.
So now that we've gone through a basis for experimentation and testing, I'm going to walk you through how we interpret and compare slime mold to existing models. In this case, our experiments are based around a central distribution center, various transit points, and outlying customers as the smallest nodes pictured on the right. We use this map to accurately allocate the quantity of oats, which are the food source, as they are placed proportional to demand and oriented by location. In this experiment, the origin of slime mold is in the central distribution center. From here, it grows outward, executing its growth just as products would move through an actual supply chain. As you can see, the slime extended its veins in the formation on the left, which was then transitioned into a graphing software to analyze its efficiency. The yellow arrows represent the shortest path an item would move from the central warehouse to a single customer, in this case being customer 6, and the length was then summed across all customers to create an efficiency metric for the network. From here, traditional network methods were used to model the same scenario. One thing we noticed is that over the course of all of our experiments, slime mold chose less and more strategic paths. Knowing this, we created an adjusted base model, which has the same number of paths as slime mold. and this adjusted model allows us to see which algorithm shows the more essential paths. After successfully growing base models, we then varied both the demand and distance to see how slime mold adapts to these factors. We repeated the same process outlined in the previous two slides. As you can see across both graphs, slime mold, the yellow bar, slightly underperformed the base model, but was almost identical to the adjusted model when taking that into account. We also found that slime mold more often than not does not connect customers and creates forked paths in highly concentrated areas.
To sum our results, we found that slime mold was slightly less efficient than traditional network models, specifically 20% less when compared to traditional models with more paths, and 4% less than traditional models with the same number of paths. In addition to shortest path length, we evaluated each network by comparing the minimal spanning tree lengths and the total distances, all of which led to the same evaluation, that slime mold is comparable. Overall, we find these results very promising as we do not conduct experiments in a lab setting and have still found that slime mold is a viable option when creating supply chain networks. For project management, the entirety of our project was definitely a group effort. From the initial idea and research that we started with last spring to the final experiments we ran this past month, we've all been able to really overcome the challenges that raised from both COVID and trying to create something we had never seen before. We were able to transform our homes into makeshift lab spaces and be able to determine the most efficient way to grow the slime mold and create these large-scale Petri dishes. Being able to adapt to remote learning was difficult in the beginning, but thank you to Dr. Dafari for being so engaged in our project and helping us through the semester. And of course, we had to mitigate risk along the way. Some of the largest risks we had was the slime mold not accepting the environment we created for it to grow in. A lot of the initial steps in this process was to control variables to make the most ideal environment for the slime mold. And another risk was taking into account the variation in the data of the slime mold and being able to interpret the slime mold's paths in our experiments. And then also the timing and documentation of the slime mold, since at different stages, the slime mold would grow at different rates. So through our findings, we believe that this can apply to even more studies, including transportation networks involving rail, urban planning, and maritime shipping. We have found that slime mold is capable of solving complex network problems, allowing us to compare this data to already established ways of solving network problems. Thank you, and please let us know if you have any questions.